Y'all can go ahead and chat me your first and last names if you want to count for a roll. Again, roll is irrelevant, but just if you want a record of it. I have other ways, of course, too, but we're going to go ahead and start in. I think last time I discussed with you maybe jumping into chapter 27, but I decided I'm going to go ahead and do the remaining examples that I think are most important from chapter 26. And I'm saying they're most important in the sense that those are the ones that might be more difficult for you guys to figure out on your own. I've left some of the simpler ones. In fact, there's a couple good ones here in the capacitor applications where you can see how you can make, for instance, uh, a repetitive signal. For instance, you can make a voltage that goes like this, a sawtooth voltage, stuff like that. You can use it to make a blinking light, not unlike the lights you see on those little sawhorses that are out in the roads at night when a road's been closed due to flooding or something like that. There's always a little yellow light that goes blink, blink, blink. So you can actually use an LED or a capacitor in parallel with a light to do that as well. There's other ways, but anyways, all that stuff is pretty interesting. So I'll leave it to you. But those examples are straightforward. So the examples I'm doing are the more difficult ones. We did solve a circuit with three unknown currents last time using Kirchhoff's loop rule and Kirchhoff's junction rule. And I explained to you how it's best to try to choose a loop that has a common current with another loop. So for instance, in that case, I had two junctions or two nodes where currents come in and leave. You always have one nodal equation for one less nodal equation than you have number of nodes. So for instance, if you had two nodes, you're only going to have one nodal equation because the other one will be the same thing and repeat. So like I1 equals I2 plus I3. If you look at the other node, it'll be I2 plus I3 equals I1. If you're assuming the left is what's going in and the right is what's going out, then you need, since it's three currents, then you need two other loop equations. And last time I did the outer loop and the upper loop because the outer loop included that top current and the upper loop also included that top current. Because they had a current in common, that allowed me to solve for the other current they have in terms of that common one so that I could have two equations, one for I1, for instance, in terms of I3, and then another one for I2 in terms of I3, and then I could plug that in the I1 equals I2 plus I3, and therefore I'd only have I3s and I could solve for it. So that's a common trick that you try to pull when you're trying to solve systems of equations. And I reminded you all that that's pretty much one of the bars for this course, almost to the point where, just like in 241, if a student couldn't add vectors, I would do everything to make sure they don't pass that class, not out of meanness, but out of you're not going to be able to survive if you don't know how to add vectors, or also how to take dot products, how to do simple integrals, how to do simple derivatives, that sort of stuff. So in this second semester, you're supposed to know how to apply Gauss's law, and then use V equals the negative integral E dot dl to find the change in voltage from one charge object to another, and then use C equals Q over V to actually calculate the capacitance. That's just a fundamental rite of passage, if you will, for this course. And you'll see if we get far enough, there's also another one where we're going to take phi equals the integral of B dot dA to calculate the magnetic flux in what it turns out to be an inductor. Then we're going to use uh, oh, that actually, before we use that, we use not Gauss's law, but Ampere's law, the closed integral of B dot dl equals mu zero times I enclosed to find out the magnetic field. Then we use the phi equals the integral of B dot dA to find the flux, and then we use an equation for the self-inductance, L equals I over phi, or excuse me, phi over I, to find the actual inductance, or self-inductance, another word for it. So those are sort of the fundamental things you got to be able to do to succeed in 242, and one of them includes, as I was saying, the ability to solve a circuit by hand. So I don't care what methods you use. You might use Gauss-Jordan, you might use Cramer's rule with determinants of matrices, or you might just use what I'm telling you. But the main thing is I welcome you using your calculator and its mathematical functions to check your work, but I'm going to have to see your work on an actual face-to-face test in solving a system of equations for a circuit. So imagine or just know that you're going to have at least one circuit where you're going to have to solve for three currents, and you're going to have to show me the algebra used to do it, and it's going to be, it might very well be one of the problems that you see in the practice test, but I might change the numbers a little bit. Okay. All right.
So,
Go
question.
ahead.
So can we expect maybe the next face-to-face test to be similar to this last one?
Yeah, that's pretty much the way the first one was sort of supposed to be as well. I won't necessarily, and I don't say too much about it because I still have a couple of students that haven't taken it, so I don't want to give anybody an unfair advantage. But I don't always do a series of problems that build up to solving one problem. I do that when I feel like I've expressed to you repeatedly that, hey, this is something really important, but history shows me students still don't necessarily get it. So sometimes I'll try to do that Socratic method where I ask a series of questions to lead to the answer for one big question. So I wouldn't find that unreasonable, for instance, to do on a test three, but I
Could
usually don't do that.
something like that be, I don't know, put into a practice test or some way
It,
we can actually practice it? Because it's nothing like that in the homeworks.
yeah,
We never had
so
a chance to do. I didn't even actually understand, starting with the first part, what you were actually asking. So
yeah,
that's
I
scripting for the next six questions.
gotcha. Yeah, that's actually exactly what I've been doing all these lectures and telling people, hey, this is what you're supposed to be able to do. You're supposed to be able to use Gauss's law to find the magnetic the electric field. Then you're supposed to use this equation to find. Again, I'm trying to generalize it so I don't give away the crux to everybody. But there's another step you're supposed to take to find something else, and then a third step you're supposed to take to find the quantity that I really want to go for. But I've literally been saying that every time I do a Gauss's law problem since chapter 21. So I agree with you. You didn't see that necessarily in the homeworks. Well, you did. It just, I didn't explicitly say, hey, do all this. I assumed you were doing it because I told you you had to do it. So, yeah, that can very much happen. I do know some students, I checked today because one of my students told me that they didn't get a chance to watch a lot of the videos. And in fact, I hadn't watched hardly any of them. So I checked, and there is a lot less people watching my video for this class. So you might want to watch it because I've been given hints like that all the time, and it's not supposed to be hints, that are secret. It's just hints for me telling you, hey, this is a fundamental thing about the course that you've got to do. I just mentioned another one a second ago, so yeah, expect that as well.
Well, see,
Uh,
I guess there might have been I might have misunderstood something from the beginning of the class then when it was told that this part was no longer essentially mandatory, that we'd be able to get the information from the books and all, not knowing that no, there actually is stuff in the videos that you will not learn anywhere else, that we will be testing you on, that if you don't see these videos, you're just going to be kind of SOL.
Well, you didn't really frame that accurately because that's exactly what the book does too. If you're looking at the book derives it the exact same way that we do, except in chapter 21 he kept one part, excuse me, chapter 22 he kept just the first step, and then when we got to the chapter on capacitance, they showed you that exact same process with every
I
one of
mean,
them.
yeah,
So
in
that's,
all the chapters, yes, it shows you how they derive the formulas, but
but they do it on every problem. It's not
I
like they
mean, but
just do it
also
once.
never once have they said, "Hey, why don't you do this?" Usually it's just like a here's a good for you to know, like here's how they get to here,
Yeah.
but all you really need to know is the formula. And up until this point, we've never had to
Yeah.
derive it ourselves.
Yep. Well, you do now. So yeah, be advised. Yeah, I mentioned that. And like I said, that was an ongoing thing. I just never had any idea that people would be forcing or allowing themselves to try to teach themselves PHY 242 without watching the instructor's videos. PHY 242 is, in my estimate, the hardest, most rigorous class we have at TCC campus, and it is brutal. It's not easy to pass. That's why I was always surprised that people wanted it online. But yeah, you gotta do that. I am currently, as I mentioned before, I'm currently working on a assignment that'll help you with that, and it's also going to help your last grade. So there's going to be an assignment. I'm about, let's say, about two-thirds of the way through. It's a really time-consuming process. I started it a couple times in the past, and it just didn't pan out. We didn't have enough memory, but now we do in my Canvas page. So now I have enough memory where I can guide you through examples like that, and I'm going to do that. And then I'm going to have a curving mechanism. Let me explain that to you. Students that make up to a 50, if they get 100% on this extra assignment that I'm going to give you guys, if you make 100% on that and you made up to a 50 on your test two, then you will automatically get a 67. If you made a 51 to a 60 and you get 100%, you'll make a 77. If you made a 61 to a 70, you'll get an 80. If you made a 71 to an 80, you'll get a 90. 81 to a 90, you'll get a 93. And if you made a 91 or higher, you're going to get just 2 points added for doing 100%. So it's a staggered curving system where everybody gets a appreciable change in their grade, and it's going to be inducive of learning or conducive to learning. So yeah, that's going to be coming up. It's just I had to make the questions myself. No one's ever done this far as I've been able to tell. I've been doing it by the videos. I even called it the paradigm repeatedly and told people, hey, you got to know this paradigm. So you still have to know the paradigm. So, anyways, we'll get to that. And I understand, Dylan. I 100% understand. I had the highest grade any student made in my 242 on this was only 88, I think, and my
I'm
241 is like a
surprised
90.
that,
But it's only like four of them total
yeah,
out of.
I'm surprised someone made that high. I
Yeah,
couldn't even figure out how to start answering them because it was the wording of the first part really confused me,
mhm.
and I was not sure where to go from there.
Yeah, that make sure. I mean, I totally get it. Yeah, the questions were not worded that way, but what I did was that question was made into like a six-part question, but it came from one question, and I just broke it up into six separate questions. And I thought I was being really nice because I'm giving you 6.25 points for each one of them, and yeah, it didn't go out so well. But don't
No,
worry, I got you guys. I'll fix your grades. When this many students make a bad grade as an instructor, we have to figure out, hey, what responsibility of this is mine? What portion of this problem is mine? And obviously, when only maybe six people out of 29 students got a B or higher, then yeah, that tells me that I've screwed up a little bit as well. So I'll get you back on track. Don't worry. But you are gonna have to do work to get up to it, and hopefully it'll help you. All right.
I just I'm having a better understanding of that is a possibility, and that without watching the videos, you won't like
Yeah.
clarifying some stuff because obviously I've had online classes, and it's usually you can get all the information you need from,
Yeah,
everything else.
I
And
agree. That's and it's awesome that you're doing that. I'd say you're coming out way better off than most students, but just because you're trying to teach yourself, if you are successful and can do well enough. But if you're not, yeah, then you definitely need to watch the videos. I just never in my life imagined students were not going to be watching the videos. It's just like I said, we're learning vector calculus. I mean, people don't take vector calculus often until they're in the fourth year of their bachelor's degree in math. So you don't even get it if you're a major other than math, usually. So that's a large part of what this course is. So definitely, pay attention to the rigor of the class. I'm not saying you did anything wrong. I'm just saying definitely need to going forward. Okay. All
yeah,
right, let's get started. And again, I'm sorry, Dylan. Your grade will get a lot better. And you're probably speaking for a lot of people. You're not, standing up and only saying, speaking up for yourself. And it's not like I'm upset with you or anything. I think
no,
it's good.
I thought it was just me until we had lab, and
Nah,
I
yeah,
talked to
it's
other people in lab, and everybody was really confused and like caught off guard. Like, and no one really understood what was going on.
yeah. Have y'all
There's a
been
lot of
working
guessing,
together like
and
a group, study group or anything? Have y'all been doing any of that?
I literally have no time.
Gotcha. Yeah,
I have a 1-year-old, and I work from 3 a.m. until 4.
yeah, it's a nightmare. Well, let's get on track, like I said, and we'll figure out what's going on. But yes, absolutely, I do not expect, and I don't want anybody trying to succeed in my class without watching the videos because I do a lot with the videos, and I happen to think as a teacher that I'm decent at explaining really tough concepts, but I can't do that if you're not watching me at all. So it's okay. We'll just get there, and I'll have to. I'd learned this now because obviously I see that students haven't been watching the video because a student told me that today, and I was like, oh wow, okay. So, well, I'll learn going forward, and you'll learn going forward. We'll all be better off. So I'm going on to example 2610. If you open your book to that example, this is at the RC circuits, resistor and capacitor in series subsection. So what we did last time was I mentioned to you that you can get a differential equation from applying Kirchhoff's loop rule to the circuit that you see right here. And when you solve that equation, you get these equations that I have listed under solution for this problem. I'm going to go ahead and share my screen so you can see that solution comment as well as the problem statement itself. I took the time to actually write it up this time instead of just allowing you to go back and forth between your book. And thanks for coming, Dylan. I'm glad you were able to fit it in. Actually, you come quite regularly, so I know it's not a I know it's not like you've been avoiding the class other than, when you can't come because you have lab or whatever. So here's the problem. It says example 2610 for the circuit shown below, find the RC time constant tau, the maximum charge the capacitor can obtain. I named that Qmax. The time required to reach 99% of Qmax, I called that T99. The current I sub Q50 when Q reaches 50% of Qmax. E, the maximum current I max, and F, the charge I Q sub I20 when I is at 20% of the maximum. So those are the typical types of questions they ask. Part of this and me doing this is that sometimes students get to the logarithm and exponent sections of their pre-calculus class and they don't necessarily get it, and they just sort of say, well, I'll just take a hit on that particular part of the test. That's the nature of physics. We sort of look through the history of every education everybody's always gotten up through calculus and even differential equations, and we look for each little niche that you didn't necessarily understand, and we're going to ask you a question about that. Uh, they really you're not allowed to skip any topics in physics, so at least regarding math. So let's get started with this one. So we have the equation Q equals CE times parenthesis 1 minus e to the negative t over tau. We've got V, the voltage across the capacitor, V sub C, is equal to the EMF times 1 minus e to the negative t over tau. And we've got I equals E over R times e to the negative t over tau. Those are the equations that would have been derived. And I said for charging because you're going to find out they're different equations when you're discharging a capacitor. And that's what the next example is about. So keep that in mind. Uh, First off, they want to know the time constant. That's the most trivial thing you can put up. I'm going to write the solution in purple just to have it stand out, I guess, mainly because I forgot to change color. But tau is equal to R times C. And I've been mentioning to you guys in electronics, it's quite normal for us not to change to the base unit and just keep the suffixes, or excuse me, the prefixes on the SI units. So I'm going to show you that here. The R is 30 kiloohms. Notice also that there's no ambiguity in me writing just 30.0 K on the circuit because the circuit has a symbol for a resistor, and therefore whatever numbers there has to be in ohms. Same thing with a capacitor, whatever numbers there has to be in farads, and with a battery, same thing there, whatever numbers there has to be in volts. So we've got 30.0 kiloohms, and we got 0.200 microfarads. A micro times a kilo is 10 to the third, a micro is 10 to the negative six. So you end up getting 10 to the negative third. So this should come out to be a milli. And when I multiply 30 times zero point 0.2, I get 3. So this should be 3 milliseconds, 3.00 milliseconds. And actually, I could keep an extra digit. As you can tell, the extra digit would be 0. So usually I don't even take the time to write the extra digit, but I did this time just so everybody will know that I'm keeping one extra digit the whole time. Uh, can anybody confirm that that's exactly what you got as well with your calculations? I'm going to do it with my calculator just to make sure I didn't make any careless mistakes. I'm sure I didn't, but
I got 6 instead of 3.
Thank you, Alex. I can't believe I did that. I don't even know where the three came from instead of the six. Uh, that's it. No more drinking before class. No, I'm just playing. All right, part B. So that's the time constant. And what the time constant is basically the time required in an exponential decay for it to go from 100% to 1 over e, basically, to that. You'll see that in a second. For part B, they want to know the maximum charge a capacitor can have. If you look at the equation for capacitance, or excuse me, for charge, you got Q equals C E times 1 minus e to the t negative t over tau. That is basically a function that starts at zero and goes up like this and asymptotically approaches a horizontal line. That horizontal line is at Q equals CE. So the actual Q max that we're asking for is Q max equals C times E. You might also notice that that's just C equals Q over V solved for Q. We're using the E because it's the electromotive force. It's representing a battery, but it's the same thing as voltage. In this case, we're going to take and multiply the capacitance, which is 0.200 microfarads, times the voltage, which is 12.0 volts. Now, 12 times zero point 0.2 is the same thing as 1.2 times 2, so this is going to be 2.40, and the result, since I have the micro in there, means the result's going to come out as a microcoulomb. So that's the answer. I've got 3 milliseconds for the time constant. I've got 2.40 microcoulombs for the Q max. Now for part C, they want to know the time required to reach 99% of Q max. And as I told you, a good fraction of this problem stuff is about me showing you how to deal with exponents and solving these kinds of equations. So if you're a little rusty on your exponents or your exponentials or your logarithms, this is a good thing to pay attention to. If we start off on part C, we're asked to find the time required to reach 99% of Q max. So what I do is I take my Q equation, which is Q equals CE times 1 minus e to the negative t over tau, and I set that equal to 0.99 because we want 99%, and 99% as a decimal is 0.99 CE, because CE is Q max. That's equal to CE times 1 minus e to the negative t over tau. So what we can see immediately is the CE cancels out with the CE on the other side, and I end up getting e to the negative t over tau is equal to 1 minus 0.99. So that's kind of helpful in that we know, for one thing, e to the negative t over tau at this point in time is going to be 0.01, because that's what I get here. 0.0100, say, is what that's supposed to be. So now I'm supposed to just solve for the actual time. And the way I do that is I take the natural log of both sides. So I take the natural log of e to the negative t over tau, and I also take the natural log of 0.01000, like that. And whenever you take the logarithm of something raised to a power, the power just comes out in front of the logarithm, and you're left with, in this case, with the ln of e, and the ln of e is just 1. So that becomes 1 times negative t over tau is equal to the natural log of 0.01. So I'm going to type in, if I can ever find my natural log function, uh, 0.01, and that gives me negative 4.605 as what the negative t over tau is. So notice that comes out to give us a positive, and we get t is equal to 4.605 times tau, which is 4.605 times RC are specifically times 3.00 milliseconds, which I could have written 3.000. Now I can multiply this 4.605 times 3.
Oh, Mr. Younger,
It's six again. Thank you.
6 milliseconds.
Thanks for catching me on that. I made the joke but forgot to make the change. Yeah, that's bad.
I had a
And
question.
yes, sir.
I had to step out for a second. What does tau stand for? Or
Tau is the symbol that we're using for our time constant. And when you solve the differential equation, it just happens to be a natural result of that. And it's R times C. So you take the resistance of the circuit and multiply it by the capacitance of the circuit, and that gives you the time constant.
okay.
In terms
So
of
so T
mathematics,
is time, but tau is a time constant.
yes, it's like that. It's related to the half-life if you're familiar with
Oh, okay.
radioactivity and that sort of
Okay,
stuff.
yeah.
Gotcha.
So
So
there's a
with
half-life in a circuit?
sort of, because a half-life is when a value drops to half of what it was originally. In the case of the circuit, we normally use, instead of one half, we normally use the 1 over e, because obviously the exponential base of the natural log is the e. So what we use instead of half-life is we use a time constant. But they're directly related. There's an equation you can relate one to the other from.
Oh,
Yep.
okay. Thank you.
No problem. So this gives me 13.82 seconds. Again, carrying, and that's milliseconds. Again, carrying an extra sig fig. That is the time required to reach, what was to reach 99% of Q max. So this is T99, I think is what I decided to call it. Yeah, that's T99. And that's just some terminology I made up specifically for this. I use it in a lot of my physics classes, but you're not necessarily going to find it somewhere in the other books. It's just a nice little easy convert or symbol to use. The part D says they want to know the current when the charge is 50% of what it's supposed to be. So this would be more like a half-life. When I find out this time would actually be the equivalent of half-life, Dylan. Uh, and you're going to see how it relates to tau in a second. So in this case, they're saying the current I sub Q50 when Q reaches 0.50 max. So Q equals 0.50 max, Q max means 0.50. Now we look at our equation. Q max we know is CE. So I write 0.50 CE is equal to CE times 1 minus e to the negative t over tau, like this. Again, the CE cancels out with the CE, but you get to see what happens. You see, for instance, that e to the negative t over tau is equal to 1 minus 0.5000, like that. And of course, that's equal to 0.5000. So when we solve for this time, that will be the equivalent of the half-life. If you wanted to use that terminology, like I said, we just don't use it in electronics. So now I'm going to take the natural log of both sides. So I take the natural log of e to the negative t over tau. Now I'm doing this because this is normally what students do, but there's a lot smarter way, and I'm going to tell you that in a second. But I'm taking the natural log of both sides. That gives me the natural log of 0.5000, like that. And the left-hand side again becomes negative t over tau times 1, because the natural log of e is just 1. Remember, y equals log base b of x implies x equals b to the y. That's the fundamental thing that everybody should have memorized, and then you can sort of sort your way through any exponential or logarithmic expression. So now I've got negative t over tau is equal to the ln of 0.500. I happen to know the ln of 0.500 is negative 0.693. But either way, you can type it in if you want, but that's a worthwhile thing to memorize. So ln of zero point 0.5 is equal to negative 0.693. And since we're using 4 digits, I'm going to go ahead and add the extra 1 on it. So that's what we have here. And now you can see that this is the equivalent of T1 half. And what you have is uh, the half-life is really 0.6931 times tau. So just as a sidebar, T1 half equals half-life is equal to 0.6931 times tau, or you can call it the ln of 2 times tau. That's the relationship. So now you know the relationship between them, and you've seen how it came about. So hopefully that helps. With this, I can now also tell you what T1 half is. Going back to my purple, T1 half, I called it T. Oh, actually, I didn't even call that anything. So I'm going to take the 0.6931 and I'm going to multiply that times the tau, which was remembering this time that it's 6.000. That gives me 4.159, and again, that's milliseconds. So what we saw was the time constant was 6 milliseconds, whereas the half life is about 4.159 seconds. We don't need this. That's not specifically what, or did they ask for that? No, this is not specifically what they asked for. What they asked for was what the current was at that time. So I'm showing you what a typical student will do, but I'm going to show you a better way in a second. Now that we have that, we now take that and plug it into the equation for the current, and the equation for the current gives us the following. I is equal to, in this case, we had E over R times e to the negative t over tau. And we can plug all this in. We're going to now say that I is equal to E over R. Now notice E over R, E is 12.00 volts and R is 30.00 kilo ohms. So when you divide a volt by a kilo ohm, that's going to give you a milliamp. So that's how I'm dealing with this. And then all of that times e to the negative t over tau. This is the part where you can realize that there's a lot simpler way. As soon as we realized that Q was equal to, or we were supposed to find the time at which Q is equal to zero point 0.5 Q max, then we knew E was going to be equal to 1/2. So at this point, I don't need to compute what that E is. I just am going to take the 12 and divide it by 30 and then multiply that by 1/2, and that'll give me exactly the right answer. So 12 divided by 30 gives me zero point 0.4, so this is going to be zero point 0.4 milliamps. But then I got to multiply it by 1/2, and that gives me 0.2. If you plug in the time in there, you'll see that you still get the same answer, and it's 0.2000, and in this case, it's milliamps, which is if we move the decimal to the right, it would be 0.0002. So that's good enough as it is. So this is I for Q50, and notice it equals I 50. In other words, it equals 1/2 of I max. Did everybody see what I was saying about the shortcut or the fast and smart way of doing it? Anybody have any questions on that? Okay, well, let's look at part E then. Part E is the maximum current I max. The maximum current I max is from I equals E over R times e to the negative t over tau. If you looked at a graph of this, it would just be an exponential decay. So the maximum the current is going to have is at t equals 0. And when t equals 0, e to the negative t is 1. So I'm just going to get I max is equal to E over R, which is what we just calculated a second ago before I multiplied by 1/2. So we're going to get 0.40 0 milliamps is I max. Any questions on that one? All right. Now I'm going to see if you guys can think of what I just taught you about the quick and dirty way or quick and easy way. We have F here, and F, they want to know what QI20 is. And I mean by that, they want to know what the charge is when the current is at 20% of maximum. Anybody have an idea what that would work out to be? Think about it a little bit and don't, I mean, I'm not asking you to necessarily answer out loud. You're welcome to, but I want you to see if you can figure it out. I'm going to go ahead and solve it now. So QI20, basically what that means is I got to figure out when I equals E over R, E to the negative T over tau. I'm going to take that and figure out when exactly is I equal to 0.20 I max. So that's 0.20 I max. Well, I'll just leave it as instead of calling it I max, I'm going to write out what I max is. We already figured out that I max is E over R, and we're going to set that to E over R times E to the negative T over tau. So we can already tell at this point E to the negative T over tau is going to be zero point 0.2. Therefore, E to the negative T over tau is equal to 0.200, and 1 minus E to the negative T over tau is equal to 0.80. So that's the big thing because now that we have that, we want to know what Q is, and Q has the other form of the exponential. It's got the 1 minus. So Q is going to be 0.80 times Q max. You can do all the calculation like I did in the previous part if you want, but this is a much smarter way of doing it, a lot much easier. But if you don't get it, then just do it brute force and hope you'll get it later. So with this, I'm going to take my Q max and multiply it by 0.80, and we can assume that's to an infinite number of decimal places because they're literally asking us for it being 20% exactly. So our Q max we found was 2.4 microcoulombs. If I multiply that by 8, basically if I multiplied it by zero point 0.1, I'd get 0.24. So this is going to be 2.4 minus 2 times 0.24. So that'd be 0.48. So 2.4 minus 0.48. That gives me 1.92 microcoulombs equals what I called QI20. So QI20 corresponded to I 80, in other words, or corresponded to Q80 or something like that. That's what we're looking at. Actually, did I say that? Yeah, QI20. Yep. Any questions? All right, so that's how you use that equation, those equations, and they are on your equation sheet. So it's not like you got to memorize them. It would help you to learn how the process that was gone through to solve that differential equation, and even to set up the differential equation they did in derivation. That being said, no, this is not the level where I would test your ability to do that. But that's a nice goal to shoot for in every subsection. If you can complete the derivation on your own, you're a little bit closer than anybody that can't do it to better understanding it. So I highly recommend you try that. I'm going to go on to example 2611. This one uses a little bit less stuff, but it is using the discharging of the capacitor. So there's a different differential equation that pops up when you take a circuit like this one, where you can imagine, for instance, I'm missing something from a circuit. I just realized that's not good. What am I missing? I think I'm missing a straight line. Yeah, I must have got sidetracked in the middle of my drawing and left off part of it. Oh, yeah, that's what it was. Uh, this line I should draw that in purple. This line right here, when the switch is at B, it allows the charge capacitor to act like the battery, and the battery is completely cut out of the circuit. However, when you switch it to A, the battery is able to charge up the capacitor depending on how long you leave it on there. If you leave it on there a long enough time, then it'll reach Q max, but that's not necessarily the case here. So when you have a circuit with just a resistor and a charge capacitor, the capacitor takes the role of a battery basically and starts to dump its power. Only it dumps its power in a more fast way, a way that's related to the time constant tau equals RC. So in this question, they're saying the circuit shown below has been used to charge the capacitor to Q0 equals C times E, and at t equals 0, the switch is moved from position A to position B. And the current is monitored. At t equals 40 seconds, I goes from I0 equals E over R to 0.500 I0. What is the value of Q0? What is the value of R? And what is Q of T equals 60.0 microseconds? So I've already taken the time to write out the solution with the discharging equations as well. So you see these equations are different. Specifically, all of these go like the number times e to the negative t over tau, whereas when we were charging the capacitor, we had V and C went like some number times 1 minus e to the negative t over tau in parentheses, and only the current was an exponential decay. So all of these are exponential decay. Let's go ahead and start with A so we can show you how to pull this off. Actually, I do like writing in a different color for the solution, so I'm going to do that again. What is the value of Q0? So what we know is Q0 is actually equal to C times E. We have the C and we have the E, so we should be able to figure out what that is. In fact, the C is 30.05 microfarads, and the volts is 30.0 volts. So 30 times 3.05 gives me 91.5. And notice I didn't change the prefix, so that comes out as micro coulombs is equal to Q0. So I'll just circle that as my final answer. Notice how I'm also writing the equation in its plain form. Like in this case, I wrote Q0 equals C times E, and then I showed myself substituting the values with their units in it. If you do that part of the problem, I'm going to give you the lion's share of the credit, and that's what I've been telling you in the last two face-to-face tests about showing your work. You're you handcuff me and don't let me give you any partial credit if you don't at least give me that first step. So it's helpful to write the solution with all the equations that you're going to use. If you find out after you're finished solving the problem that you didn't use one of them, just put a line through it and I'll know that you knew better than to have to use that. All right, now we've got that. For part B, they want to know what is the value of R. So what we have here to help us with that is tau is equal to RC. That's our time constant. And we also know that I is equal to I0 times e to the negative t over tau. And we finally know that at 40 microseconds, I think that was the number. Yeah, at 40 microseconds, I0 was zero point 0.5, or I was zero point 0.5 of I0. So I'm going to write 0.5000 I0 is equal to I0 e to the negative t over tau. And you can see again the I0s cancel out. And what this tells us is that, oh yeah, this tells us is what we can find tau to be. Because we know up here this t is 40.0 microseconds. So plugging this in, I now have 0.500 with an extra sig fig, or extra digit, not sig fig, and that's equal to e to the negative 40.0 times 10 to the negative 6 over tau. Now, you know exactly what the answer is going to be uh, because Dylan asked a few minutes ago about the half-life, and this is really what we're finding is we're finding the half-life. So it should be equal to the ln of 2 times tau. So the ln of 2 times tau, where tau is RC, and that should get it for us. But let's go ahead and show you the work. We're going to take the ln of both sides, 0.5000 is equal to negative 40.0, using an extra digit here, times 10 to the negative 6. Mike, that's seconds now since I put the 10 to the negative 6 over RC. And we don't know R, but we do know C, so I'm going to go ahead and put in C is 3.05 times 10 to the negative 6 farads. So I can go ahead and solve for R, and what we're going to get is R is equal to 40 divided by 3.05. And now I'm going to divide that by the ln of 5, which has got a negative right now, and the ln of point 0.5, I said the ln of 5, the ln of point 0.5 is 0.6931 negative. That's going to take care of the negative, so we end up getting just R is equal to uh, 13.11 divided by, that's one extra digit again, divided by the negative of, well, I'll just say divided by 0.6931 with obviously one extra digit. And that gives us R is equal to 18.92. And as it's drawn, we did have farads, so this is just going to come out in ohms, not kilo ohms. And it's got one extra digit that's not a sig fig. And that's that. Any questions on that one? Now, my numbers are different from the one that your book is doing, so you shouldn't expect to get the exact same numbers that they did. But you can check and see that the physics is done right. I'm trying to give you another example so you can still work the book example and be, excited when you get the right answer. I've done part C. Now we're going to do part B. Now I'm going to do part C. And part C asks, what is Q at t equals 60.0 microseconds? So Q is equal to Q0 e to the negative t over tau. That means Q at 60.0 microseconds is equal to Q0, which we already found was 91.50 microcoulombs, times e to the negative t, and t is 60.0 times 10 to the negative 6 seconds, divided by the time constant. And the time constant we can now figure out, since we know R and we know C, that's going to be 18.92 ohms times C, which we know was 3.05 times 10 to the negative 6 farads, like that. And that should give us Q of 60 microseconds is equal to 91.5 times. Now I'm going to take my E and I'm going to raise it to the negative 60 times 10 to the negative. Actually, I'm going to cancel out that 10 to the negative 6 because I don't even, I have it in the top and the bottom. So I'm not even going to use that. I'm just going to say negative 60 divided by parenthesis 18.92 times 3.05. That's the equivalent of canceling out the 2 micros. And this gives me 32.35. And since I put that in microcoulombs, this should come out in microcoulombs as well. Any questions on that? And Alex, did you get any different numbers than I did, or did you get the same numbers?
That looks about right. I want to
Sounds
say.
good. And I'm always, fat fingers sometimes make careless mistakes, so I want to make sure matching up. And I appreciate anybody that's doing calculations alongside me because that is helpful to you and to me. Anybody have any questions on how to solve these circuits? As you'll see in your book, there's a couple more examples. There's example 2612, where it's asking you about how quickly does voltage drop, and then there's another one where they're showing you a conceptual example where you can use a light with a switch. And it says in the circuit of figure 2619, the capacitor is originally uncharged. Describe the behavior of the light bulb at the instant switch S is closed until a long time later. That's a really good description. And then you look at a gas-filled tube in parallel with a capacitor, and you get a nice little sawtooth voltage. That's just another application of capacitors. So the author has done a really good job in giving you applications in fields other than our own so that you can learn more about how the world works as well as learn more about the fields you might choose to go into, whether it be medicine or whatever. So feel free to ask me questions, but I try to stay away from those because I don't know how interested people are in them, but they are something that you should read no matter what, independent of whether you're going to major in that stuff, because it'll help you be a more knowledgeable and competent person. So the next section was 26.6 electric hazards and safety. And obviously, I want you guys to be safe and stuff like that. So I do want you to read it and think about it and all that good stuff. But this one luckily doesn't have any examples. It's just a subsection that I'm not covering. So you will not see any questions from examples in that section if there were any or any other things. So we're going on now to section 26.7, which is ammeters and voltmeters, measurement effects, quantity measured. So what we're going to do here is I'm going to show you how to design a ammeter or a voltmeter. Before I do that, I've got to give you a little idea of exactly how a galvanometer is made. So when you guys had your electric field mapping lab, you used a galvanometer. That was that really light little uh, gauge, if you will. It was made of plastic. It felt like it was a piece of junk, and it really is a simple little piece. That's why it's so light. But basically, what it was a device where you had a terminal that you can connect uh, a wire to, and then another terminal where you can connect another wire to. And what happens is when you connect a wire to one of them with a current going in it, like this, then what happens is inside of the circuit, there is a wire that this wire is equivalently connected to, and it wraps around a iron rod like that. And in fact, that iron rod has some springs attached to it to hold it perfectly straight when no current's going to it. So this those two little springs keep it vertical, and you have some ability to adjust it so if it's not exactly vertical or not exactly on the zero, you can adjust the springs and the tension in them. But when a current runs through it, then you have a north end of a magnet over this end, and you have the south end of a magnet on this end. And when you start to run a current through there, then the current, after it goes around that metal, it comes back out to here, and out goes the current. Now, current can come in the other side, and when that happens, it's going to cause the needle to deflect the opposite way. But when it's going in the left, it's going to deflect to the right. So then all you have to do is graduate. In other words, run some test amounts of current through the wires and then mark off where 50 microamps is, where 40 microamps is, where 30 microamps is, where 20, 10, and 0 are, and then do the same thing on the other side. By doing that, you've made a very simple device that is somewhat related and scaled. It's actually, scaled so that you can get a measurement of microamps, and it's a very simple device to make a galvanometer. Now that we have that, we know certain things about it. It has, for instance, a max current. It also has a internal resistance, which you can measure. I'll say, for example, 50.0 microamps. Amazon's here, Shawnee. And it also has a Vmax, which is really it's not intended to measure V, but it can measure V. So for instance, the scale normally has, 10, 20, 30, 40, 50, but it also might have 5, 10, 15, 20, 25 still with the other scale too, so that if you design it to have its max current up to 25 microamps or something, or you design it to have your max voltage up to 250 volts or something, then you can do that. The Vmax is just I max times R, which in this case, I'll say, for example, uh, 3.00 ohms, and in this case it'd be 50.0 microamps times 3.00 ohms, and that gives you obviously 150. Whoa, all of a sudden the thing started acting like it was trying to make neat drawings out of my handwriting, and I did not tell it to do that. So that's 150.0 microvolts. So that's the normal information you're given. You're normally not given the voltage, by the way. You don't normally not given that Vmax. You're just given the internal resistance and the max current that it measures. But the trick is, and this is what I'm trying to teach you with these two examples, you can take this galvanometer, which is one of the first devices we scientists and my that were my ancestors were able to make, and it obviously was limited to go up to like 50 microamps or something like that. But then they would encounter, hundreds of amps or tens of amps. How do you do that? Well, not only that, can you use it to measure voltage? Well, you can measure voltage and current with this, and that's what I'm going to show you how to do. You can even dial it up to measure the size of the current that you want or the size of the voltage that you want, almost up to any value, almost. Okay, so let's go on to example 2614. 2614. So example 2614 says design an ammeter to read 1.0 amps at full scale using a galvanometer with full scale sensitivity of 50 microamps and a resistance of R equals 30 ohms. Check to see if the scale is linear. Okay, so we want a ammeter ammeter with full deflection at I equals 1.00 amps if galvanometer, uh, almost wrote that capital, galvanometer has Imax equal to 50.0 microamps and R equals 30.0 ohms. So that's our plan. Now, the big trick here is when you're trying to make an ammeter, you need a small fraction of the current, specifically when you have a full current of 1 amp coming into the device we're making, we want 50 microamps, excuse me, of that to go through the galvanometer, and we want the remaining part of the 1 amp to go through the wire that's parallel to it. So the way we make an ammeter is you're going to imagine an ammeter is like this with a circle with an A in it, and you just have two terminals to connect to it, sort of like Theven and Norton equivalent sort of stuff, where you just think of it as two objects in a black box or two terminals in a black box. This is going to be the equivalent of basically a wire that comes in, and then it reaches a node. The node takes the resistor and the galvanometer like this, but in parallel to that is what we call a shunt resistance, which we won't write the word shunt every time. We'll just write sub S. But this is a shunt valve basically. So if you have y'all ever heard of the word shunt or a shunt valve or anything like that before? I don't see anybody chatting anything. The typical scenario that I recall is my wife often tells me about, she doesn't tell me about personal patients or anything, but one of the things she looks for when she does cardiac sonography is she looks for a shunt, a decrease in pressure. So when your heart ventricles are squeezing, the one half is supposed to deliver the blood to your lungs so it can get oxygenated, but the other ventricle is supposed to supply your whole body, and that's the one that's under the higher pressure. And if it gets so high pressure that there's a hole opens up between that ventricle and the other, then we're said to have a shunt valve, basically allowing the pressure to decrease and go against the pulmonary side instead of the body side. So that hole, which is what we call a PFO or patent foramen ovale, is a part of your sort of your evolution in that when you're in utero, your heart is more or less just a two-chamber object, not a four-chamber, because there's a valve that makes the two ventricles one. And I think it might even be that you have something connecting the atrium. I can't remember that. I don't know that anatomy very well. But anyways, that's what we're doing here. And in this case, we're treating this the same way. We're letting most of the current go through the shunt valve, and then only the amount of current that we want go through the other one. Now, in order to do that, we realize that we have the galvanometer and the resistor in parallel with the shunt resistance. That means the total voltage across the two has to be the same. We know that Ohm's law gives us V equals IR, so we can use that. And what we're going to say is V galvanometer has got to equal V shunt. And with that in mind, we're going to say I galvanometer times R is equal to I shunt times R shunt. That's the big equation that we have to have true in order for this to work. Now, the other thing we need is we need I galvanometer. For full deflection, it has to be 50 microamps, so that's 50.0 microamps, which we can also write as 0.0005000 amps. That's what the current through the galvanometer is, and we want I through the shunt to be 1.0000000 minus 0.0000500, like that. So we do that subtraction, and you can see, for instance, we get a 0 here and a here and a here. Here we have to make this into a 10. That makes this digit into a 9, this one to a 9, this one to a 9, this one to a 9, and this one to a 0. So we get 0.999 amps. And that's the current through our shunt. So now we can say 50.0 times 10 to the negative 6 amps times 30.0 ohms is equal to 0.999950, and that's amps as well, times R shunt, and therefore we can get R shunt is going to be equal to, if I multiply 50 times 10 to the negative 6, we already know what that's going to be. That's going to be 150.0 microvolts divided by 0.999950 amps. So 150 divided by 0.99995 gives me 150.008, and that comes out in micro ohms. So I get 0.0000150.0, or actually not point, just leaving a space. Notice how I write my numbers in pods of three. Please always do that if you're turning anything in with multiple zeros. That works out to 0.000150 ohms. That's the actual shunt resistance that we need. We could call that, actually, is that right? 1.5. Oh, yeah, I did 30. That's right. Did I use the same numbers they did? I did 50 microamps. They did 50 microamps. Yep. So double check my work here. It looks like I should have, it looks like I might have one extra zero in there. This should be 0.001 and then 50. Anybody double check me on that? I'll say 50 times 10 to the negative 6 times 30. Now I'm going to divide that by 0.99995. Yep. I don't know if I did the math in my head and that's what made the mistake, but yeah, I was off by one decimal place in here. But I'm fixing it now. So that's 001, then a space, 500, then a space, zero, like that. And that's ohms. You can imagine that's a hard resistor to come by. The smallest resistance I've ever seen sold is a 1 ohm resistor. Uh, but luckily, you can put any number of resistors in parallel with one another, and the way the parallel resistance equation works, the resistance of the whole will be smaller than the smallest resistance on there. So if you take 1 ohm and put it in parallel with another 1 ohm, you end up getting 1 over 1 plus 1 over 1 is equal to 1 over R. That gives you basically a half a ohm. If you did a third, you could get 1 over 1 plus 1 over 1 plus 1 over 1. That gives you 3 over 1, and therefore you get your resistance of 1/3. If you did 4, it gives you 1/5, fourth. If you do 5, it gives you 1/5. So we're getting smaller and smaller. You can see that you can just keep doing that. You don't have to start with 1 ohm resistors. You can use, any ones you want. You just have to keep putting them together in parallel until they're small enough to use as our shunt resistance. So our shunt is going to be zero. Well, we'll just call it like this: 1.50 times 10 to the negative 3 ohms. The other thing you got to keep in mind is when you're actually designing something like this, the resistance isn't enough. Every resistor and virtually every device you buy, capacitors, inductors, they have maximum limits of how much power they can deal with. So you'd also need to calculate the power. In this case, for instance, a whole 1 amp is supposed to be going through the shunt resistance. So the power for that one should equal 1.00 amps times squared times the R, which is 1.50 times 10 to the negative 3 ohms, like that. I'm using P equals I squared R, by the way. I could have used IV, but I didn't know V, and I could have used V squared over R, but again, I didn't know V for that one. Obviously, this result is 1.50 times 10 to the negative third watts. Luckily, that's not too big of a deal because most of the smallest ones I ever find is like an eighth of a watt, 0.125, or maybe a quarter watt, 0.25. All of those are plenty big. So that's the other thing you need to be able to do is make sure that you have the right power associated with your LED or your capacitor or your resistor or your inductor. Anybody have any questions on that? All right, the last example, and then I'm going to let you guys go. Again, I'll remind you, I might send out an email tomorrow with a video for you guys to watch that I want you to watch, and it's in exchange for uh, just trying to get us caught up a little bit better. And I want to give you more time to understand some of the topics, but I haven't decided yet whether we'll do that. So if you don't get an email by Friday, don't worry about it. But if you get one sometime Friday, I ideally want you to have watched that before you come to class on Tuesday or before you attend my lecture Tuesday. So let's go to example 2614. In this case, we're going to use the exact same galvanometer. So I max galvanometer is 50.0 microamps. The resistance of the galvanometer is 30.0 ohms, and Vmax again, something they normally don't give you, but I'm giving you well, no, I won't even give it to you. We'll do it in a second. It's not a big deal. Uh, but what we want to do now is we'd like to design a voltmeter. Design a voltmeter that shows maximum deflection at V equals 15.0 volts. So that's our plan. Okay. Now, in this case, remember with the ammeter, we had to put up a little node and we had to break off the current so that 50 microamps could go to the galvanometer at the same time the other 0.9995 went through the shunt resistance. In the case of a voltmeter, what we need is the resistance to come up before it runs into the resistance of the galvanometer because we need that resistance to cut the voltage down enough so that I only have V max across the galvanometer, but the other remaining, like if V max was, we know for instance, V max was, I think, 1.5 microvolts or 15 microvolts, somewhere around there. Well, we would want the 15 volts minus 15 microvolts, we'd want that to be dissipated across the resistance that we put in series with the voltmeter or galvanometer. So again, I'll show you that we have a voltmeter like this, and that voltmeter is represented by a terminal that runs into a series resistor. So I'm just going to call this R, and then it runs into the shunt or the galvanometer resistance. Just lowercase r is what I've been using, and then that runs into the galvanometer, and then there's your terminal. What we need over this whole thing is we need the entire voltage across it all to be 15 volts. So 15.0 volts is equal to that. So we can just use Ohm's law, V equals I times R, and we're going to use the fact that resistors in series add. So we're going to say 15.0 volts is equal to I, which for this we want a full deflection when it's 15 volts. So we need the whole 50 microamps to go through there. So I write 50.0 microamps times R plus the 30.0 ohms like that. So what I can do now is take 15.0 volts and divide it by 50.0 microamps, and that's going to be equal to R plus 30.0 ohms. And when you divide 15 by 50 times 10 to the negative 6, you end up getting 3 times 10 to the fifth times 10 to the fifth ohms. Now, obviously, 3 times 10 to the fifth ohms is 300 kilo ohms, and that's more or less completely infinite compared to the 30 ohms. So you might say R is equal to 300,030 ohms, but it's close enough to just say R is approximately equal to 3.00 uh, or excuse me, 300.0 kilo ohms. And that's close enough. Okay. So that's how we would design it. Of course, we'd also need to figure out exactly what the power is. This one is not a big deal because the power is only going to be related to 50 microamps going through. So if you multiply 50 microamps times squared times the 300 kilo ohms, you still get well, we'll just do it with the calculation. So PR should be I squared R, which is going to be uh, 50.0 times 10 to the negative 6 amps squared times 300 times 10 to the third ohms. When I do this math, I get 50 times 10 to the negative 6 squared times 300 times 10 to the third, and that gives me 0.000750 watts. So that's the power requirement you should have. Again, that's pretty small. I was a little worried because it was 50 squared, but then multiplying it by 300,000. But I completely forgot that it was squared. That's why I was thinking the magnitude might be a little bit bigger, but that's still not an appreciable magnitude. By the way, they asked whether the scale was linear. What you can see from this is the current, and we're talking 2614 as well as 2615, 26. Oh, that was 2611, I think. No, it was 14. Okay, so 14 and then 2615. Making it linear, basically all you have to realize is that I through the shunt resistance is equal to R over RS times the galvanometer resistance. And that's what shows it's linear. You can sort of see the same thing here. The voltage across the galvanometer, V galvanometer, is basically just well, that includes the R. It's basically just the part that is the 15 volts minus the 15 microvolts. So with that equation, you can see that's also linear. Anybody have any questions on that? All right. I don't see anybody. The class is done. You got 2 minutes. But go ahead and chat me your first and last name if you haven't done so already. I want to remind everybody I do have a few students that did not figure out or did not take one or two online tests. I've opened those online tests up again. This time they're open until Sunday, and every one of the students that missed them had, in fact, ooh, I don't know what's going on here every every one of the students that missed them, I've opened them up at least once before. In a couple cases, I've opened them up twice before, and they've missed them. If a student misses an online test that I've opened up again, it will stay at zero. I'm not giving anybody another chance. So it's your responsibility to please go online, look in your tests, and look to see if you missed any online tests. The important thing is not to just go to a random site in the Canvas website, but to go to the modules, and any tests that you see in there, unless they explicitly have someone else's name on it, those are tests you're supposed to have done. If you've done them, then pat yourself on the back, you're done. If you have any of them that you don't have a grade other than zero in, then that means you need to do it. And I supposedly have opened not only that online test up, but I've also opened up the corresponding practice test until Sunday of this week. So you have until 11:59 p.m. on Sunday to get all of those online tests done, and you have access to the practice test, so you can still practice before doing it. If you miss this one, like I said, it will be a zero on those grades. Pay close attention to in the near future. Obviously, if I don't email you by Friday with a new link to a video to watch, then you don't have to watch a video. But there may be an assignment that I send you that is going to allow you to give you more points on your second face-to-face test. So keep an eye out for that. Hopefully, I'll be finished with that tomorrow and I can send it out then, and y'all could work on it over the weekend. But I wouldn't make it just this weekend. I'd probably make it not due until Friday of next week. So y'all have a good one, everybody. Have a nice weekend. Stay safe. Have a nice Easter, all that good stuff if you celebrate that. Passover, all those good things. Have a good day, and I'll wait for the last person to leave in case anybody has any questions. Hey, Alex, did you answer a question no or something? Because there's a big no on your name.
What's up? Oh, is it still there? Oh, I
Yeah.
thought that was temporary. So no,
I,
you said, are there any questions? And I'll try to figure out if I
oh,
can
cool.
send an emoji.
Yeah, I wondered if it did that. So that's actually helpful. I was just curious. Oh, now I'm
Yeah.
drawing on my piece of paper and I don't know how. Okay. Any other questions, Alex? Or I shouldn't say any other questions. You had any questions, Alex, before you leave? I might have muted myself. Let's see.
Oh, sorry, I didn't realize I was muted. No, I'm
Oh,
okay. Thank
okay.
you.
Well, have a good one and keep an eye out for your emails, everybody.
No problem. Have a good weekend.
You too. Let's see. Stop share. I don't know why I'm drawing on that. Okay, that's good. All right. Bye, everyone. Have a good day. Have a good weekend.